Okay. So, good evening and welcome to this problem solving session for the NPTEL course Foundation Engineering. So, those who are new to this session, so as a brief introduction of me, so myself, Shikshankar Nandi, I am pursuing my PhD in the Department of Civil Engineering at IIT Kharagpur, and I am one of the TAs for this particular course. So, today we are in week 3. So in the last week we had solved a couple of problems regarding different in situ test for subsoil investigation, and among those we can name a few like standard penetration test, cone penetration test, then a pressure meter test, then what can I say? Uh, Pressure meter, dilatometer test, and minimum wind shear test, so on. So these are from the penetration test, and apart from those penetration tests, we solved a few problems regarding the seismic refraction test. So seismic refraction test is one of the programs which we need to know for geophysical exploration. So in addition to seismic refraction, there are seismic reflection and seismic crosshole test also. Okay. So in the last week uh, we basically took two problems as homework problem. So as I can remember, the first one was regarding the determination of critical distance in case of seismic refraction test. Critical distance in the sense that is the distance from a source to the receiver at which this critically refracted wave and the direct wave will basically arrive exactly at the same time. Okay, so we basically derived the expression, but we didn't determine the numerical value for the particular data given to that problem. So in addition to that, we also took one homework problem as the pressure meter test. This pressure meter test, we had given all the data, and we had to determine the pressure meter modulus or the Maynard's modulus. So we discussed in details how to calculate or how to utilize those data to calculate the Maynard's modulus. Okay, so I hope you solved those problems at your home. So still, if you basically face any kind of problems, please let me know. Otherwise, we will basically proceed with a new topic, that is nothing but the bearing capacity of shallow foundation. Okay. So please quickly let me know if you have any problem regarding those two problems. Otherwise, we will proceed further with this new topic, bearing capacity of shallow foundations. Okay, someone is saying that my voice is low. So is it clear now? Hello? Can you please ensure me whether I am
No, sir.
okay? Okay, let me just fix this problem. Hello? Is it fine? Hello?
मतलब yes, sir. Sound is clear, sir, but it's very low, sir. मतलब I can't able to hear.
Okay. So any other participant who is facing the same problem? Okay, so the problem still remain persist or it's improved? What is your opinion? Hello. Hello.
Sir, voice is still very low, sir.
Okay. I don't know what is the problem. Just please give me some time. Hello. Can you please ensure me now whether it is improved or not? Hello.
No, sir.
Okay. So I don't know then basically what is the problem, because I have changed the settings for audio.
Sir, can you remove your earphone at once? Then you can try.
Huh.
So I think if you will keep your mic at your nearby your mouth, then it will be
Okay.
audible.
Okay. So okay. I'm trying that. Okay. So is it fine, Mr. Prem?
So it's fine now.
Okay. Thank you.
Yes, sir. I think earphone is not proper.
Okay. Then from next session onward, I have to think about that. Okay. So for this time being, please bear with me. Okay. So as I was discussing that we basically started learning a new topic, that is bearing capacity of soil foundation. Okay. So now this term. Okay, so again, I am assuming that the homework problems given to you, you are perfectly fine with that. Okay, so assuming that, I am proceeding. Okay, so foundation. Okay, so this is basically a part of a structure, or essentially a substructure, which basically transmits the load from a given superstructure to the underlying soil mass. Okay, so suppose. So this is the column, and this carries a concentrated load Q, and this Q load is basically distributed through this footing. So this is the column and this is the foundation. So this is the subsoil. Okay, so now the load which is coming from the superstructure through this foundation, it will get dispersed through this footing, okay, over a larger soil mass beneath the foundation. So this is the main functionality of this shallow foundation. So it will basically aid or help in safe dispersing of the load which is coming from the superstructure. Now this foundation can be of two types. So this is the depth of foundation, that is the distance from the ground surface to the base of the footing. So this is called depth of foundation, as you know, and this is the width of the foundation, B. Now depending on the value of ratio df by b, we can divide the foundation in two categories. So what are those two categories? First one, shallow foundation, and the next one is deep foundation. So if df by b is less than 1, so it will be under this category, shallow foundation. Otherwise, if it is greater than 1, so it will be under deep foundation. Again, deep foundation can be of two types, moderately deep and highly deep. Okay, so those are not the part of this discussion, so we'll discuss about those in the subsequent sessions. Okay, so now this shallow foundation again can be of four types. First one is the strip footing or continuous footing. Okay, any problem?
Hello, sir. Am I audible?
Yes.
Sir, I wanted to ask one thing, that we only consider the width of the foundation of that particular footing, not the whole. Like if we are making a building, so we will consider the width of the foundation will be the whole building width, or the only this column.
Can you please repeat the question?
Sir, I'm asking that we consider width of the foundation only the footing which we are putting inside the soil, only we consider the width of that thing, or we consider the depth, the whole area on which we are constructing.
No, in from which sense you are basically asking this question? So
basically, sir, if I am calculating say bearing SPC, like bearing capacity of soil, basically. So when you are like, we consider the width of the footing, the column which you are putting, only that width, not the whole area on which we are putting the column.
Okay, so I have basically got your question. What you are trying to say, please correct me if I am wrong. So when we are basically determining the bearing capacity of a footing, we are only dealing with the breadth of the footing, not the length of the footing. Am I correct?
Yes, sir. You can. Yes, sir.
So the bearing capacity expression only involves the term which is basically this dimension B, not L. So suppose if we consider a rectangular footing, suppose this dimension is B and this dimension is L, then you are saying that we are basically determining the bearing capacity of this footing only or solely based on this term B. There is no provision for L. Are you saying like that?
Actually, sir, hello? No, sir. Actually, I am trying to say that suppose that if we are constructing a superstructure on an area of 30 meter into 20 meter length, like a rectangular area.
Yeah.
Okay, sir. So we have to put columns in that.
Yeah.
For the superstructure, basically. So this, you are talking about this column only. So you are taking that we consider width of the footing of the each column. Which will be the width of the footing? 20 meter or the column width only?
No. Width of the footing. Okay. So I think you are doing one mistake in visualizing the problem. Okay, so basically, first of all, you have to distinguish between two terms. Suppose this is the plan area which you are rightly talking about. So 20 meter by 30 meter. This is 20 meter suppose, and this is 30 meter. Now, in this area, now as per the design, you need to construct some footings. So some small footing. Okay, so this is from the design point of view. So designer basically recommended that there will be 9 number of footings or 10 numbers of footings. Okay, and again, what kind of footing you are using, that is also coming from the, I will discuss in later. So what are the factors which will basically guide this design process. Now what you are basically confusing, that this plan area and this footing area are different. Is it same? So this plan area 20 meter by 30 meter, this is basically the entire area over which the building or any superstructure will be built. Now this footing is a basically part of that area. This will not basically cover the entire area. This area, small area, this is not the whole area. This is not equal to the whole area. Now in one case only, this area, this footing area will basically cover the entire area, or it will be equal to the entire area. That is only for mat or wrap foundation. So it is like an inverted slab. Roof slab we have seen. So roof slab, it is like an inverted roof slab. So this is the slab type of thing. Then these are the footings. Okay, so a continuous slab will be there. There will be no gap. So here we can see that in between these two footings, we can see a gap. So this is not concrete portion or the materials of the footing. This is only the soil filling. So after construction of the footing, we have to fill the soil. Again, backfill the construction site. So are you getting my point?
Yes, sir. So what will be the width of footing in this case, which we are explaining?
In this case, the width of footing will be the shorter dimension. Suppose this footing has 2 dimensions. So this is one dimension, dimension 1, and this is one dimension, dimension 2. The shorter of these two will be the width of the footing.
So basically, sir, we will calculate for bearing capacity for each footing which we are putting inside the soil.
Yeah. So if that's okay, so let me explain from this point of view. So if in a superstructure, suppose there are 20 number of columns. Now if each column is basically will giving you the same amount of upload. Okay, suppose 400 kilonewton is basically passing through each column. Now what will happen? And again, the subsoil is of the same nature. Suppose from the field investigation, we have determined that it has a safe bearing pressure of 180 kPa. Now what will happen? To resist or to sustain this kind of load, the dimension will be same. Yes or no? How? That will basically learn in the subsequent lectures, because so far we didn't learn how to design a footing. So design of footing is basically still
Sir,
sir,
I want to sir, actually in that case, that if we are putting a raft foundation, like you are saying that in case of raft foundation, the width will be 20 meters. Suppose the width is 20 meters. Sir, so is and our we are constructing like we are digging 10 meter depth. So is it a shallow foundation or is it a deep foundation?
No, again, that will be decided upon the ratio of df by b. If df by b ratio is less than 1, obviously it will be shallow foundation. It will be under the category of shallow foundation. And mat foundation, if you see that the breadth is also very high. You are talking about that, what is the dimension of that wrap? 20 meter or 10 meter?
Sir, suppose that the dimension of the raft is 20 meter into 30 meter. Okay, sir. And we have made the foundation at 10 meter depth. So is it a shallow foundation or is it a deep foundation? What will you call it?
It is obviously a shallow foundation because here B is 20 meter and DF is 10 meter. Now what is the ratio of DF by B? It is less than 1. It is 0.5 only, na? 10 by 20. It is 0.5. So it's less than 1. So it's essentially a shallow foundation. We cannot say that this mat foundation is falls under the category of deep foundation.
Suppose if we are doing like this spread footing or isolated footing, and in that case our footing is of 2 into 3 meter dimension. So width will be like 2 meter, and we are digging up to like 10 meter depth. We are making a foundation at 10 meter depth. So in that case, it will be a deep foundation or shallow foundation.
Okay. Now let me come into from the perspective of feasibility. So you are basically constructing a footing of dimension 2 meter by 3 meter and at a depth of 20 meter. Is it feasible? So what will be the construction process? What will be the construction process then? So you have.
I think, sir,
like if we are doing,
yes.
Okay. Sir, like if we are not like if we are doing only up to 6 meter, then in that case, is it feasible, sir, or not?
Even 6 meter also, this is a very high depth. And please remember that first you have to excavate the soil, then you have to basically, what you have to do? You have to construct the footing, then you have to backfill the site. Suppose what you were talking about, so this is your DA, okay, and this is your B. Now if this DF is very, very high, so you are basically unnecessarily tending this problem to a deep foundation by anyhow increasing this DF. But you have to also keep in mind that this footing should be feasible. You have to think from the economic perspective also. So you cannot design in such a manner that the construction cost will basically increase means 2 times of or 3 times of the superstructure. Or I am not basically going about any number, but it should be feasible. When you are basically as a designer, as a geotechnical practitioner, you are basically giving a design for implementation or for execution, various aspects you need to fulfill. Okay, so it's very good that means if you go basically deeper inside the soil, you will be having a good quality soil mass. The strength of the soil mass will be much higher as compared to the superficial layer, because as we know that superficial layer is basically having low density. So as we basically go deeper, the relative density and the corresponding shear strength parameters will basically increase. So that means we will always try to place the foundation at a depth where it will be having a reasonable strength. The underlying stratum will be having a reasonable strength. But it doesn't mean that you are basically constructing a footing of this dimension df by b at a very high depth. So essentially you have to backfill. It may arise in the situation or circumstance may be like that you are not having the adequate strength at a shallower depth. You are not having the adequate strength at a shallower depth to sustain the load which is coming from the superstructure, because this load is predefined. This load you cannot change or you cannot edit. The load is basically given to you. So depending on that, you have to basically or accordingly you have to design the footing. Now, if a shallow foundation is not feasible from the economic point of view, obviously you have to go for deep foundation. Then we have to basically study what kind of deep foundations are there, like pile foundation, well foundation, and so on. I hope you may.
Thank you, sir. I got your point.
Okay. So you cannot design means anything. Okay. So depending on the load and the subsoil properties, if shallow foundation is not a solution, it's not a feasible solution, feasible in the sense it will have to resist the load which is coming from the superstructure, and at the same time the design should be economic, it should be economical. Now if this is not satisfied, then you have to think for some other alternative solution, and it may be in the form of deep foundation. So for that, to provide this 2 by 3 meter at a depth of 6 meter or 10 meter, it will be very much essential to provide a circular pile foundation. Okay, so depending on the scenario, you have to adjust your design. Okay, so that for that only this concept of or in-depth knowledge of shallow foundation or any foundation is very, very essential for any geotechnical engineer. Okay, but again please keep in mind that from the economic point of view, the first choice to any engineer is the shallow foundation, because the construction cost for shallow foundation will be much lesser as compared to the deep foundation. Okay, so this is the first choice to any practicing engineer from the economic point of view. So, and it is very clear that this depth of foundation is very less. It's less than this width of the footing. Okay, again this width of the footing, suppose you are not increasing the depth of the footing, you are only increasing the width of the footing. So in that case, suppose this is the plan area 20 meter by 30 meter and you have 10 number of columns. Now the footing basically designed for one particular column, it's overlapping with the footing of another column. Now what will happen? So in that case, you can basically design a combined footing instead of isolated footing. Isolated in the sense only one column will be supported by one individual footing. Now in that way we have designed, okay, so for a particular project. Now this has come to our notice that the footing of one individual column is basically overlapping with the footing of another individual column. Or again, there is a scenario or circumstance that there is a boundary line. So you cannot basically extend your footing area beyond this boundary line. So this is the boundary line and there is a column near this boundary line. So you cannot extend this footing beyond this boundary line because this property doesn't belong to you. So in that case also, you can basically think for this type of combined footing. Okay, so two footings are basically combined by a single footing, two or more footings. Now in this way, if the cover area of all the footings basically exceed a certain percentage of the whole plan area. Okay, so I cannot recall at this point what is that figure or number. So in this way, if the footing area of all the footings basically exceed the plan area by a certain percentage, then this concept of individual isolated footing or combined footing again will not be feasible. So instead of that, the construction of mat or a foundation will come into picture in that case. So instead of one isolated or combined footing, there will be a continuous slab, and that slab will basically support all the footings, all the columns in that superstructure. Okay, so in this way, now these are the solutions under shallow foundation. Now any of the solution is not feasible to your project, so then you have to think for alternative solution like deep foundation. Am I clear to you? Hello.
Thank you so much, sir. Thank you, sir.
Okay. Okay, so already we have discussed this terminology. So what is strip footing or continuous footing? So in that case, basically the length of the footing is much higher than the width of the footing. Okay, so it basically supports something, a load bearing wall. So in the load bearing wall, so it's basically continuous in any particular direction. So the footing which can support this kind of structure, that is called strip footing. Then spread footing or isolated footing, so it will basically for individual column or two columns, then combine more than one, and mat or wrap foundation. So it is a continuous slab or footing, so which will basically support the entire structure. Okay. Okay. Now this design, coming to the design perspective, so just as a little small introduction, okay, so we will not discuss in much details. So this design will be guided by, okay, so again before that, so these are the selection criteria for any specific shallow foundation. So this shallow foundation is basically decided by the magnitude of loads, nature of subsoil strata, already discussed, the nature of the superstructure and specific requirements. Okay, you can basically go through the lecture materials which are released on the course portal. Okay, now coming to the basic criteria for design of foundation. So these are the two basic criteria. So one is the bearing capacity criteria, or we can also say shear failure criteria, and the next one is supplement criteria. So when you will be designing a foundation, so the foundation can safely transfer the load from the superstructure to the subsoil, so that there is no possibility of shear failure. Again, there is no possibility of excessive settlement of the superstructure. So it cannot be like that we have basically designed a footing and this footing is safe against shear failure, but it is not safe, or rather it can undergo an excessive settlement. So an excessive settlement can take place due to the application of this load coming from the superstructure. So you need to basically bother about both the criteria, so bearing capacity criteria and settlement criteria. So from the bearing capacity criteria, we will be ending up with it is called the safe bearing capacity. Okay, safe bearing capacity. We'll explore this term, what is meant by this safe bearing capacity. And from the settlement criteria, you will be getting what is called safe bearing pressure. Okay. Now lesser of these two will basically govern the design, and it is known as allowable bearing pressure. Okay, allowable bearing pressure, and this value will be given to you, and based on this value, and if this is not given to you, then you have to exercise for that, because it is a job, it is our fundamental job before designing a foundation for a particular given structure, superstructure. Okay, next, to determine the bearing capacity, we have, since there are two criteria there, so first one is the bearing capacity criteria and second one is the settlement criteria. So in today's session, we'll mostly discuss about the bearing capacity criteria, and accordingly we'll solve a couple of problems. Now under this bearing capacity criteria, when the load is basically coming from the superstructure, so this underlying soil, the subsoil, can fail in shear in this mode. The first one is the general shear, the next one is the local shear, and the last one is the punching shear. Now by that time all of you know how this mode of failure is defined, because this is defined based on some typical features or characteristics of the load settlement behavior of the underlying soil. Am I correct?
Yes, sir.
Okay. So those who are still pending for brushing up this concept, so please go through. Okay, I will request all of you, please go through. So what are the typical features of general shear failure, then for local shear failure or punching shear failure, or when this case is feasible. Okay. Then we have basically learned different bearing capacity theories. So in the literature, you can basically go through a lot of theories which are basically proposed time to time by different researchers. So the first one is Terjagi's theory, then Skempton's theory, Meyerhoff's theory, Hanson's theory, Basics theory, IS-code method, and based on some SPT correlation provided by Teng. Okay, so these are the few theories which we have learned from this specific way. Now this theory is basically will give you a different bearing capacity, and I hope you basically you all have the idea that our professor basically solved one problem considering all these theories, and from that it is very clear that when you will basically design, you need to consider all these theories and accordingly you have to decide. Okay. And finally, we have learned about a few factors which can influence the bearing capacity, like relative density, width and depth of the footing, unit weight of the soil, and position of the groundwater table. Now, how these factors will affect or influence the bearing capacity, please go through that. Okay. So, suppose we can take the example of width and depth of the footing. So this width and depth of the footing, we cannot say that the geometry of the footing will be a factor, influencing factor for any kind of soil. Any kind of soil in the sense cohesionless soil, cohesive soil, or cohesive friction soil. So in case of cohesionless soil, what is your opinion? So width and depth of the footing will influence the bearing capacity or not?
What, sir? Repeat once again, sir.
In case of cohesionless soil, width and depth of the footing will influence its bearing capacity or not. Suppose we are constructing one footing on the cohesionless soil deposit.
Yes, sir.
So the dimension have an impact on its bearing capacity.
It will impact on bearing capacity.
Okay. Then in case of cohesive soil,
it will also impact.
Okay. So what is the expression for general expression right now I am talking about, that Q is nothing but CNC plus Q NQ plus half gamma B N gamma. Now first of all, for cohesionless soil, so as you are saying, it will be having an impact on its bearing capacity. Now for cohesive soil, what is the value of phi? It would be 0, purely cohesive soil. So it will be, the phi value will be 0. Now if phi value is 0, so suppose as per Tirjagi's equation, what are the bearing capacity factors? At least please keep in mind these values corresponding to phi equals to 0 and corresponding different bearing capacity theory. Suppose I am talking about Tirjagi's bearing capacity. Now what is the value for NZ? It's
5.14.
Sorry, 5.14 for Meyerhoff's theory. Okay.
Yes.
Okay, so according to Tirjagi's theory, it's 5.7 and N2 is 1 and N gamma is 0. So as you can see, this third term will vanish. That means if you increase the width, so there will be no impact on its bearing capacity. And it is valid for cohesive soil only, because the phi value is 0. So similarly, you can draw conclusion for depth.
Cohesionless soil, phi equal to 0.
Huh?
For cohesionless soil, phi equal to 0.
For cohesionless soil, phi equals to 0. How?
Yeah. If for sand, it is phi equal to 0. It is cohesionless soil.
No. For sand, how phi can be 0?
So no, sir. C. I am telling about C.
Okay. Okay. For obviously cohesionless soil, there should not be any cohesion. Okay. So cohesion would be 0. But right now I am talking about cohesive soil. Okay. So for purely cohesive soil, if you draw the more Coulomb failure envelope, so it will be something like that. This is tau, this is sigma n. So this is your undrained cohesion. And the mode circle would be like, if you draw the mode circle for unconfined compressive strength, it will be like something like that. Okay. Okay. So accordingly or subsequently, you can draw the conclusion for depth of footing as well. Okay. So for a specific type of scenario, the depth of footing will be having no impact on the bearing capacity. Okay. Please check, because you can expect this type of statements or this type of questions in many competitive exams. Okay. So already we have spent much time on this part, so we'll not spend any more. So we'll directly take a few numerical problems. So we'll start this problem solving session first. So by taking a few problems from GATE examination. Okay, so the recent GATE examination, that is GATE 2023. So a square footing of size 2.5 meter by 2.5 meter is placed 1 meter below the ground surface on a cohesionless homogeneous soil strata. Considering that the groundwater table is located at the base of the footing, the unit weights of the soil above and below the groundwater table are 18 kilonewton per meter cube and 20 kilonewton per meter cube respectively. And the bearing capacity factor NQ is 58. The net ultimate bearing capacity of the soil is estimated as 1706 kPa, and the unit weight of water is given as 10 kN per meter. Now earlier, a plate load test was carried out with a circular plate of 30 cm diameter in the same foundation pit during a dry season, when the water table was located beyond the plate influence zone. Using Terzaghi's bearing capacity formulation, what is the ultimate bearing capacity of the plate? Now this is somehow a reverse scenario. I don't know whether so by that time you are having the idea of plate load test or not. So do you have any idea for plate load test? How to conduct and what are the properties you can extract from this kind of test? Have you any idea? Okay, so this is also a subsoil in situ test. So we can basically get the load deformation behavior, the load settlement behavior for the subsoil. Okay, so suppose this is the load and this is the settlement. So I will not go in much details about this test, but a few things which you should know for solving this problem. So first of all, the circular square plate basically placed on the soil, for which this type of load deformation behavior you are determining, and this plate is basically then subjected to some loading. So it will be cyclic or it will be gradual. Okay, gradual in the sense monotonic loading. Monotonic means you are basically increasing the load in a monotonic fashion, and in the cyclic case, suppose you are applying first some 5 kilonewton load, or in terms of stress or pressure 5 kPa. So at an increment or at an interval of 5, then 10, then 15. So first you start from 0, then 0 to 5, this is one cycle. Then you again reload. Okay, so you unload the plate, then again you apply 0, 5, 10, and then again reload, then reload 0, 5, 10, 15. So in this fashion, so this is called cyclic, and another is monotonic. Okay, so where you are continuously increasing the load 0, 5, 10, 15. So there is no unloading and reloading. Okay, so now from this test you will be having a clear idea about the bearing capacity for any specific size of footing which you are going to construct on that soil. So this is one purpose or one objective of this test. Okay, so first of all, you will be having the load settlement behavior of the underlying soil, as well as you can predict the bearing capacity of a specific dimension of footing which you are going to construct on this soil. Okay, now this is from the test perspective. So you basically first you have conducted the plate load test, and on the basis of this test data you are predicting the bearing capacity for any different size of footing. But from the problem perspective, so it's a different scenario. So here a square footing of size 2.5 meter by 2.5 meter, the ultimate bearing capacity of the soil, it's given to you. It's 1706 kPa. Now you have to determine the bearing capacity for the same soil, for the same foundation pit, for a circular plate of diameter 30 centimeter. And there is a change in the field condition. Now what is that change? So when you have determined the ultimate bearing capacity of the soil for a square footing of size 2.5 meter by 2.5 meter, so in that case the groundwater table is located at the base of the footing. So it is very essential or important to note. However, when you are determining or when you are conducting the plate load test, at that time the influence zone, the plate influence zone is completely dry, because this is a dry season. So the test basically conducted during a dry season. So this is one change in the water table location between these two scenarios. So accordingly, you have to determine the ultimate bearing capacity of the plate. Okay, so we'll see how to calculate. So here we have to use the Terjaghi's bearing capacity theory. Now for Terjaghi's bearing capacity theory, sorry, so for Terjaghi's bearing capacity theory, so as you know that this theory is basically primarily derived for a strip footing, a long continuous strip footing. But here we can see that this is a square footing. So we have to accordingly apply or implement the shape factors, okay, the correction due to shape. So what is the expression, modified expression? So first of all, QU, this is alpha 1 CNC plus gamma DF NQ plus alpha 2 gamma B N gamma. So this alpha 1 and alpha 2 are nothing but the shape factors. Okay, now how to calculate? So alpha 1, it is 1 plus 0.3 B by L, this is for a rectangular footing, and alpha 2, this is 1 minus 0.2 B by L multiplied by 0.5. Okay, so both are given for rectangular footing. Now since we are dealing with square footing, so square in the sense B and L are equal. So this alpha 1 value would be 1.3 and alpha 2 it would be 0.4. This is for square footing. Okay, so therefore the expression will be modified in this fashion, that 1.3 CNC plus gamma DF NQ plus 0.4 gamma B N. Now please read the statement very carefully, that this footing constructed on a cohesionless homogeneous soil stratum. So that means the C value is 0. The first term will vanish. Okay, so let me draw the problem definition here. So this is the df this is df, and again the groundwater table is located at the base of the footing. Now this is B, this is 2.5 meter, and what is about depth of foundation? It is 1 meter. Okay, so C value is 0 and phi value it is not given, rather the bearing capacity factor corresponding to the surcharge contribution, it's given as 58. Yeah, and the unit weights, so below and above the water table, so below is, so gamma is 20 kilonewton per meter cube, and here gamma is 18 kilonewton per meter cube. Okay, so please let me check. Above 18 and below 20. So this first component will vanish. Now since this water table is basically located at the base of the footing, so you have to implement the water table correction factor as well. Now how you can implement the water table correction factor? So there are different ways, but what we have learned from this specific course, so we'll basically act in that way. So first of all, there is two terms, two unit weight terms. So this is 1 and this is 2. Okay. Now if the water table is at the ground surface, so in that case both these terms will be affected by the water table. Now I am basically talking about the different possible scenarios for the groundwater table. Now if the groundwater table is located at base of the foundation, then this term will not be affected, because this term indicate the surcharge contribution, this unit weight or the stress which is basically imposed by this soil of height or depth dA. And as you can see, the water table is located at the base of the foundation, so there will be no effect in this zone. Whether this soil below the foundation will be completely submerged, and accordingly you have to consider the effective unit weight in the calculation, or submerged unit weight in the calculation. Further, if the water table is located beyond a depth of B from the base of the footing, then none of this term will be impacted by the groundwater table. So I basically talked about 3 scenarios. So first one, when the water table located at the ground surface, both of these terms will be affected. When it is basically at the level of foundation, then only the second term will be impacted, and when it is located at a depth of dA plus B from the ground surface, or simply B from the foundation level, then only the second term will, none of this term will be impacted, and in between then you have to interpolate. Okay, so that we'll see in the subsequent problems. Okay, so here it's very straightforward. So the water table is located at the foundation level, so only this unit weight term in the third expression will be impacted. Okay, so QU we can modify in this fashion, that gamma dF NQ plus 0.4 gamma prime D N. Okay, now there is a question, why this dimension is chosen as B? Because it is observed that the failure zone is basically restricted up to this depth from the foundation level. Okay, so due to the application of load, there is the possibility of failure. Okay, so if the load is basically increased reached a stage when the underlying soil is basically fail in shear. So in that case, the failure mechanism which will basically develop inside this soil mass. So the extent of this zone, so something like that. So this is the base. Okay. So I hope you all know about this. Something like this. So three zones are there. This is the elastic zone. These are the radial shear zone, and these are the passive zone. Okay. Now this extent I am talking about. So this is restricted to B. It is observed from the field investigations. Okay. So that's why it is restricted to B. Okay. So this is called the influence zone. Now, so this way we can modify the ultimate bearing capacity expression. Now please see very carefully that in this expression all the entities are known to you except the N gamma factor. Okay. So therefore we can easily determine the N gamma from this equation. So it will be QU minus gamma df NQ divided by 0.4 gamma prime. Now we'll substitute the values. So QU, this is given as 1706. So 1706 minus this gamma value. This is for above the water table. Okay. So please be careful. So we have to take this, or we have to substitute this values only. 18 multiplied by 1 multiplied by the NQ factor is 58 divided by 0.4 gamma prime B. Now what is the value for gamma prime? So this unit weight which is given for soil below the water table, it signifies that it is for the saturated soil mass. Okay, so this is the saturated unit weight, and gamma prime indicates this is submerged unit weight. So how to calculate submerged unit weight? Submerged unit weight gamma prime we can calculate by subtracting the unit weight of water from the saturated unit weight. So therefore it will be 20 minus 10, therefore 10 kilonewton per meter. So this will be 10, and the width of the footing is nothing but 2.5 meter. Okay, so please calculate. Okay, I think I did a mistake. So this is not for ultimate bearing capacity. This value 1706, this is not given for ultimate bearing capacity. This is given for net ultimate bearing capacity. Okay. So therefore, we have to basically take the help of the net ultimate bearing capacity expression. So Q N U, and it is UU minus gamma D. Okay. So now we can determine, so this term, this N gamma term, this will be QU minus gamma df So because QNU is given to you, okay, so this expression we can substitute here. So QNU, if you substitute here, sorry, so therefore this will become gamma TF NQ minus 1 plus 0.4 gamma prime. Now please calculate N gamma. N gamma will be 1706 minus gamma value is your 18, df value is your 1, nq 58 minus 1 divided by 0.4, gamma prime 10, b 2.5, and n gamma we are calculating. Okay, so n gamma it would be 60. Okay, so we have calculated the n gamma for the given subsoil condition, that is a cohesionless homogeneous soil stratum. Now what we have to determine? We have to determine the ultimate bearing capacity of a plate of 30 centimeter diameter. Okay, so now coming to the determination of bearing capacity, ultimate bearing capacity of the plate of 30 centimeter diameter. So again you have to apply the correction factor for the shape of the footing. So it's circular now. For circular footing, this alpha 1 it will be same as for square, but alpha 2 it will be 0.3. So it will be 1.3 CNC plus gamma df NQ plus 0.3 gamma B N. Okay, now this part will vanish, so remaining only second and third part. So gamma, again please keep in mind that we are basically dealing with the same deposit, same foundation pit. Now one thing that you have to keep in mind, that when this plate load test is constructed in a pit, test pit, so this soil in this pit is basically excavated. So there is no surcharge. Suppose this is the plate, this is the circular plate. So adjacent to this plate or at the plate level there is no surcharge. So therefore this component also will be 0. So leaving only the third component, that is 0.3 gamma N. Now in this case you are conducting the plate load test in a dry season, so gamma will be simply this value 18 kilonewton per meter cube, and B, this will be the diameter of the plate, that means 0.3 meter. This is the B value. And N gamma we have calculated from the bearing capacity, net ultimate bearing capacity of the square footing, and this is 68. Since the soil deposit remains same, so if you calculate, then you will be getting the ultimate bearing capacity of the plate as 110.16. Okay, this would be the. So now we'll take another problem, and this is again taken from GATE examination 2023. So in this problem, a square footing is to be designed to carry a column load of 500 kilonewton, which is resting on a soil stratum having the following average properties. Bulk unit weight is 19 kilonewton per meter cube, angle of internal friction is 0 degree, and cohesion 25 kPa. Considering the depth of the footing as 1 meter and adopting Meyerhoff's bearing capacity theory with a factor of safety of 3, the width of the footing is. Okay. So a few assumptions are also given to this problem, which are shape and depth factor. So these values you can take or you can assume as unity, and the groundwater table at greater depth. So the main objective of this problem is to determine the dimension of the square footing which can sustain this column load of 500 kilonewton with a factor of safety of 3. And here we have to use the or employ the Meyerhoff's bearing capacity theorem. Now we'll see how to solve this kind of problem. So first of all, we need to determine the safe bearing capacity, the net safe bearing capacity of the footing. Okay. Now how we can determine this net safe bearing capacity? So this is nothing but net ultimate bearing capacity divided by factor of safety. Okay. So this will basically assure you there will be no chance of shear failure. So now how we can determine this Q nu? So net ultimate is nothing but ultimate minus this overburden at the foundation level, that is gamma df divided by. So this is the net safe bearing capacity. Now if we multiply this net safe bearing capacity with the footing dimension, okay, so assume that B, this is the width of the footing. This is the width of the footing which we have to determine. Okay, so width of the footing, for this time being we are assuming this B. Okay, so what will be the area then? The area of the footing will be simply P times B, since this is a square footing, that means P square. Now if the net safe bearing capacity is QNS and this is the area, then how much amount of load it can support or it can sustain? So QNS, it will be capital Q, that is the load, so it will be the capacity multiplied by its area, that is P square. Okay, and it should be equated to 500 kilonewton, because this much amount of load the column is basically applying to the square footing. So therefore the determination of this net safe bearing capacity is very much essential to address this kind of problem. And how we can determine QNS? So to begin, we have to first calculate the ultimate bearing capacity of the footing. So as per Meyerhoff's theory, the bearing capacity expression will look like this, that QU, it is CNC, SC, DC, IC, and then it's Q, NQ, SQ, DQ, IQ plus 0.5 gamma B, N gamma, S gamma, D gamma, I gamma. Now what are these additional terms? As we know that C is the cohesion, Q is the surcharge at the foundation level, NC, NQ, this NC, NQ, N gamma. So these are the bearing capacity factors. Bearing capacity factors. Then SC, SQ, S gamma. These are the shape factors. And DC, DQ, D gamma, these are the depth factors, and IC, IQ, I gamma, these are the inclination factors. Okay. So for this problem, this shape and depth factors values are given to you as unity. So this value, all these values would be 1. Here also all these values would be 1. And again, this column load means from the internal friction point of view, you can determine. So if you assume that this load is basically applying concentrically and vertically, so there is no inclination, so this is 1. Okay, so this is purely cohesive deposit because the angle of internal friction value is 0. So therefore, as per Meyer, so phi equals to 0 and C equals to (25 kPa). Sorry, this cohesion value is your 25 kPa. So from phi equals to 0, so as per Meyer, the bearing capacity factors are, so NC is your 5.14, NQ is 1, and N gamma is 0. So therefore, this third term will vanish. So only there will be first and second terms. Okay. Again, this NC, you know, so this is 5.14, and this NQ, this is 1. Now we can easily calculate the ultimate bearing capacity. So it will be 25 multiplied by 1, 5.14, then 1 plus Q. Now what is about Q? So Q, so this is the surcharge at the foundation level. So foundation depth is your 1 meter. Okay, the depth of the footing is your 1 meter. And what is the bulk unit weight? 19 kilonewton per meter cube. Again, you need not to bother about the groundwater table. Why? Because groundwater table is located at a greater depth. Okay. So therefore, this Q, it will be simply gamma times dF, and gamma means the bulk unit weight of the soil. So bulk unit weight of the soil is 19 kilonewton per meter cube. So 19 multiplied by dF is your 1, and then again SQ, DQ, IQ 1, 1, 1. Okay, plus the third term is your 0. So if you calculate, then this value would become 147.5 kilonewton per meter cube. So therefore, Q net safe, it would be QU minus gamma dF. So QU is your 147 minus 5, gamma dF again 19 into 1 divided by, what is the factor of safety value for this problem? It's 3. So 3. So 147.5 minus 19 divided by 3, 42.83. So this is the net safe bearing capacity. So you can easily calculate the required footing dimension. So it would be simply, so from here you can determine the V value as 500 by root under 500 by QNS. Okay, so 500 by approximately 3.43. So you need to provide the footing width as 3.42 meter from the bearing capacity criteria. Okay. Now I have basically put some tables in this slide. Now this table will tell you about the different factors: shape, depth, and inclination. Now, why these factors are, or this table is given or presented in this slide? Because in this problem, it's explicitly mentioned that you can assume the applicable shape and depth factor values and unity. Now, if the statement or this kind of statement is not mentioned in the problem, then you have to consider these factors as per this table. That means you have to calculate these values: shape factor, depth factors, and inclination factors. Okay. So in this way you can determine the required dimension of a square footing, where the load for the supporting column is given to you, the subshell properties are given to you, and the required or recommended factor of safety is also given to you. And again, this problem is taken from recent GATE examination 2023. Okay. Now we'll take another problem from GATE 2016. So where a 4-meter wide strip footing is founded at a depth of 1.5 meters below the ground surface in a C5 soil as shown in figure 1. The water table is at a depth of 5.5 meters below the ground surface. The soil properties are the effective cohesion value is 35 kPa, effective internal angle of friction is 28.63 degree, the saturated unit weight is 19 kN per meter cube, bulk unit weight is 17 kN per meter cube, and the unit weight of water is 9.81 kN per meter cube. The values of bearing capacity factors for different 5 are given below. Using Terjagi's bearing capacity theory and a factor of safety of 2.5, the net safe bearing capacity for local shear failure of the soil is. So in the previous cases, we have considered the general shear failure. So here we have to consider local shear failure. Now, what is meant by local shear? So in case of general shear, if we observe the load settlement behavior or plot, then you will be having something like this kind of plot, where the peak load is clearly defined. Okay. However, in case of local shear, this kind of behavior means here the collapse will be abrupt, catastrophic, and sudden. And this is mostly valid for dense sand or steep type of clay. However, for local shear, which is the mode of failure, prevailing mode of failure for medium sand, so here you cannot locate the peak load. Rather, the load is continuously increasing with the settlement. Something like of this kind of plot you can expect for local shear mode of failure. So now from the failure zone in case of local shear, so this failure zone is only defined, is clearly defined only below the foundation, and adjacent to that, this is not clearly defined, it's poorly defined, and again there is a slight bulging as compared to the general shear failure. Okay, so therefore you cannot assume the mobilization of the shear strain, cohesion, or friction angle for the entire length of the failure surface. So what Terjagi considered, Terjagi is basically assume that the mobilization of the shear strain parameters in this fashion, that mobilized cohesion is 2/3 of the available cohesion, and again the mobilized friction angle, the tan 2 phi tan phi of m, it is 2/3 of the Okay, C and phi are the available cohesion and angle of internal friction. So therefore, it's very important to calculate these values first. Okay, so Cm value would be 23.33 kPa, because C prime value is given as 35 kPa, and this phi m mobilized friction angle, it would be tan inverse 2/3 tan phi, and it would be approximately 20 degree. So accordingly, you have to choose the bearing capacity factors NC, NQ, N gamma. So corresponding to phi 20 degree or phi m 20 degree, so these factors you can easily take from the given bearing capacity chart. Okay. Okay. And again, since this is the strip footing, this is a case for strip footing, no need to apply the correction for shape factor. So QU, it would be simply CNC plus gamma DF NQ plus 0.5 gamma B NQ. Now this water table location, as mentioned in this problem, it is basically at a depth of 5.5 meter from the ground surface. Now, what is the influence zone? So the influence zone is of depth or dimension B or height B from the foundation level. Now, what is the value for this B? So it is 4 meter, and the depth of foundation is 1.5 meter. So 1.5 plus 4, that covers the entire 5.5 meter, which is the distance of the groundwater table from the ground surface. So that means for this problem also, you need not to bother about the groundwater table effect, because it is located beyond the influence zone of the footing. Okay. Okay. Now, corresponding to local shear failure, these values would be, this expression will be modified slightly in this fashion. This would be Cm Nc prime, then gamma Nq prime, and N gamma prime. Now what are this Nc prime, Nq prime, and N gamma prime? So this corresponds to the bearing capacity factors for the mobilized friction angle value. So the available value is 28.63 degree, but the mobilized value is 20 degree. So you need not you need to basically calculate the bearing capacity factors corresponding to 20 degree, not corresponding to 28.63 degree. Okay, since it's clearly mentioned in the problem that you have to calculate the net safe bearing capacity for local shear failure. So this Nc prime, it is 17.7, then NQ prime, it is 7.4, and N gamma prime, it is 5. And what is the value for gamma? Okay, first DF. So DF is 1.5 meter, the width of the footing is 4 meter, and gamma value is, gamma in the sense gamma bulk. Okay, because in between this 5 meter there is no water table, so that means 17 kilonewton per meter. Now it becomes very easy for the calculation of ultimate bearing capacity. So Cm is 23.33 kPa multiplied by 17.7 plus 17 multiplied by 1.5 multiplied by 7.4 plus 0.5 multiplied by 4, 17 multiplied by 4 multiplied by, So if you calculate them, it will be so 771.64 kPa, but this is not the final answer because we have to report the net safe bearing capacity for a factor of safety of 2.5. So we have only calculated the ultimate bearing capacity. Therefore, we can calculate the net ultimate bearing capacity in this fashion: QU minus gamma dF, 771.64 minus 17 into 1.5. So which will be, I hope, 746.12. Please check, okay? And finally, the net safe bearing capacity. So this is QNU divided by the factor of safety, 746.14 divided by, here the factor of safety is 2.5. Okay, so this value, so it would be 298.46 kPa, and this is the final answer. Okay, so through this problem, we have learned that how to calculate the net safe bearing capacity of a given strip footing of with 4 meter, and this footing is basically constructed or founded at a depth of 1.5 meter below the ground surface, and the subsoil properties are also given. The recommended factor of safety value is also given, but please keep in mind that here we have to consider the shear mode of shear failure as local. Okay, so local shear failure we have to consider. Again, if it is not mentioned in the problem, then we can also refer the angle of internal friction value. So as we know that for purely cohesionless soil, this local shear mode will be prevailing for this relatively medium dense sand. Okay, so where this angle of internal friction value is less than 29 degree, and general shear failure will govern when the angle of internal friction value is greater than 36 degree, and in between you have to consider a mixed type of case, that is you have to interpolate this, you have to consider both this general and local, and then you have to interpolate the values. So mixed type of behavior you can expect. Now this is only for the purely cohesionless deposit. Now for this problem it is not purely cohesionless, so it's a cohesive frictional deposit. Now cohesive frictional deposit, this prediction will be based on the load settlement behavior. So if the failure is basically taking place at very small strain level, that is less than 5%, then you can expect, okay, general shear failure is basically prevailing. However, if there is no failure for the range of strain in the order of 10 to 20%, okay, so there you are not basically observing any kind of failure, or you are observing failure beyond that range, so it will be governed by the local shear failure. Okay, so for cohesionless deposit you can predict, or you can basically what I can say, you can basically decide the mode of failure based on the relative density or the angle of friction, internal friction values. Okay, so if it is less than 29, it will be local, If it is greater than 36, it will be general. However, for cohesive frictional deposit, you have to consider the load settlement behavior or the stress strain curve for determining the mode of failure. Okay, so since in this problem it is clearly or explicitly mentioned that you have to calculate the self bearing capacity and self bearing capacity for local shear failure, so you need not to bother about that kind of stress strain characteristics of the given soil. Okay, so now we'll take problem 4. So again, this problem is taken from GATE 2021. So in this problem, a rectangular footing of size 2.8 meter by 3.5 meter is embedded in a clay layer and a vertical load is placed with an eccentricity of 0.8 meter as shown in figure 2. Okay. Take bearing capacity factors NC, NQ and N gamma. So the values for bearing capacity factors are given. The values for shape factors are given. Depth factors, inclination factors, all are given. And again, you have to utilize the Meyerhoff's method and you have to calculate the load that can be applied to the footing with a factor of safety of 2.5. Now we'll see how we can solve this problem. So one fundamental difference for this problem with the previous problem is that, so in the previous problems we have seen that there is no eccentricity of the load which is basically coming from the column or the superstructure. But in this problem, an eccentricity of 0.8 meter is observed. So you have to accordingly consider the concept of useful width. Okay. So basically, according to this concept, you have to modify the width of the foundation if this is eccentricity along the width direction, and you have to modify the length also if the eccentricity along the length directions. Okay, so you need to first figure out whether the eccentricity is one way or two ways. So if it is one way and along the width direction, then you have to correct or modify the width. If it is along the length, not along the width, then you have to modify the length. And it is along both the directions, width and length, means two-way eccentricity, then you have to correct both the dimensions, that is width and depth. Now how? So this is recommended by Meyerhoff. So this is the plan view of the given footing. So the given footing, rectangular footing of size 2.8 meter by 3.8 meter. So this is the length dimension 3.5 meter and this is the width 2.8 meter. And the eccentricity is basically 0.8 meter, okay, along the width direction. Okay, so as you can see, this is the eccentricity. So this is the eccentricity 0.8 meter. Now, what is the fundamental of this correction? So the fundamental of this correction is that, so you need to modify the area, or you have to calculate the effective area in such a way that the loading which was originally eccentric, now it becomes concentric with respect to the effective area. So this is the fundamental behind this kind of modification. Okay, so how this modification has been done? So the modification has been done in this way. So if the eccentricity persists along the width direction, then you have to consider the modified width as the original width minus 2 times of the eccentricity along that direction. And the eccentricity is along the length direction, then the modified length will be original length minus 2 times of the eccentricity along the length direction. However, for this problem, the eccentricity basically observed along the width direction only, and we have to modify the width only. And after modification, this is the effective area. So initially the area was B times L. Now the effective area becomes B prime times L. So the width has been modified so that the load which was eccentric with respect to the original area, it now becomes concentric with respect to the effective area. And all, please keep in mind that all the shape factors, depth factors which are basically involved for solving this problem or for solving the bearing capacity, you need to implement or you need to use this modified area only. Okay, so you cannot use the original width. However, for the given problem, these factors are directly given to you. So therefore, there is no additional task for considering this modified width and calculating the shape, depth and inclination. Okay, so you can directly utilize or employ these factors from the problem statement itself. Okay, so now we'll see how to calculate the load that can be applied to the footing with a factor of safety of 2.5. So first we'll try to calculate the net safe bearing capacity, and as you know, this is nothing but the net ultimate capacity divided by the factor of safety, and again the net ultimate bearing capacity is ultimate bearing capacity minus the overwater pressure at the foundation level, that is gamma times Tf divided by this is the factor of safety, will give you the net safe. Okay, now this QU as per Meyerhof is the general bearing capacity expression is CNC SC DC IC plus Q NQ SQ DQ IQ plus 0.5 gamma B N gamma S gamma D gamma I. Okay, so all these values are given to this problem, directly given to this problem. So then we can easily substitute these values in this expression. So QU, so C. So what is the value for C? So the C value is 40 kPa. Okay. So this is 40 times NC. Now what is the value for NC? NC is 5.1. That means this is purely cohesive soil, plain. Okay, 5 value is your 0. So 5.14 multiplied by SC. SC is your 1.16. Okay, so I think it will be easy for us if we basically summarize the given data here. So SC is your 1.16, then SQ 1, S gamma 1. These are for safe factors. Then DC 1.1, DQ 1, D gamma 1. Okay, and coming to IC, IQ, I gamma, this are all 1. So now it becomes very easy to substitute. So it would be 1.16, 1.1, 1. Q value, that is the surcharge at the foundation level. So this value, this is gamma times Tf. Now the gamma value is given as 18.2 kilonewton per meter cube, and the Tf value is your 1.5. So 18.2 multiplied by 1.5, then NQ, the bearing capacity factor is your 1, multiplied by DQ 1, SQ1, DQ1 and IQ1. Okay, now this third part, as you can see from the data, given data, this N gamma, okay, I think I have done one mistake here. So this N gamma, value, it will not be 6.8, because this is 5 equals to 0 soil. So obviously this value should not be 6.8. Okay, so let me check. So now what would be the ultimate bearing capacity value then? So 40 into 5.14 into 1.16 into 1.1 plus 18.2 into 1.5, 289.65 kilometer per meter square. Okay, so before that, please let me check the original question from where I have taken. Yeah, I did a mistake here. Okay, so please correct this. So this value, this n gamma value, so this will be 0. Okay, so please just note this correction here. So it will be 0. And it's quite obvious because for phi equals to 0 soil, as per Meyerhoff's theory, NC 5.14, NQ1 and N gamma, it should be 0. Okay, so therefore this third term will not be there. Okay, so it will automatically vanish. So QU we have calculated. Now Q net save will directly calculate. So 289.65 minus 18.2 into 1.5. This is the overburden pressure at the foundation level, divided by what is the recommended factor of safety? 2.5. So if we calculate, then it would be 104.94 kilonewton per meter square. Okay, so QNS, that is the load, safe load, which can be applied with a factor of safety of 2.5 would be this net safe bearing capacity multiplied by the footing area. Now what is the footing area? So it would be B times L. So this is B and this is L. So it would be QNS multiplied by B multiplied by L. So that means 104.94. Now you have to basically you have to be very careful. Now this expression will be valid only when there is no eccentricity. If there is no eccentricity. However, this is not the case for this problem because an eccentricity along the width direction is observed and the eccentricity value is 0.8. So accordingly, you have to modify the original area, and we have already done that. So the original area was B times L. Now the effective area becomes, after modification, B prime times L. So B prime is the modified width. Now therefore the applied load that can be means the applied load with a recommended factor of safety would be this is QNS times B prime times L. Okay, since this is a case of one-way eccentricity. Now what is the value for QNS? So QNS value is 104.94. So 104.94 multiplied by this B prime value is your B prime value. It would be, I think, total or original width is 2.8 minus 2 times into 0.8, that means 1.2 meter. Okay, so this should be 1.2 meter, 1.2, and L is your 3.5. And again, this is the concept of useful width. And this is for one-way eccentricity. So 104.94 multiplied by 3.5 multiplied by 1.2. So it will give you the safe load that can be applied with a factor of safety of 2.5 is 440. Okay, so this is the answer. So through this problem, we have seen how to modify the original dimension of the given footing when there is an eccentricity of the applied load. And you have to be very careful for modifying the dimensions as per the nature of eccentricity, whether it is a case of one-way eccentricity or two-way eccentricity. Okay. Okay, I hope there should not be any confusion or doubt. We will take our next problem, that is problem 5. So square footing is founded on a pure clay deposit. The depth of the foundation is 1.3 meter and the width is 4 meter. The unconfined compressive strength of the clay is 125 kPa. The bulk unit weight is 17.2 kg per meter cube. Now what is the gross safe bearing capacity of the foundation considering factor of safety equals to 3? Use Kempton's analysis. So far we have solved problems considering this Terzaghi's theory and considering Meyerhoff's theory. So through this problem we'll learn how to implement the Kempton's analysis for the calculation of bearing capacity for purely clay deposit. Okay, so it is important to note that Kempton basically provided the bearing capacity equation or the bearing capacity theory only for purely clay deposit. Okay, and this analysis is valid for any depth of the footing. So in the previous scenarios, means for the Terzaghi's analysis case, the analysis is valid only for the depth of foundation less than or equals to the width of the footing. So that means for shallow foundation case only. However, you can use the Kempton's analysis for any value of the depth of foundation. Okay. Okay. Now, as per Kempton, you can calculate the net ultimate bearing capacity in this fashion: Cu times Nc. Now, what is Cu? So this is the undrained cohesion, and Nc, this is the bearing capacity factor from the cohesion contribution. Now, the undrained cohesion of the given clay deposit you can calculate from the unconfined compressive strength of the clay, because Cu, you know, this is half of the unconfined compressive strength of the clay. So that means it would be 125 divided by 2, that means 62.5. Okay, so this is the undrained cohesion of the clay deposit. Now, what's about the bearing capacity factor from the cohesion contribution? So for Nc, Kempton basically had given various expressions for various type of footings and for various depth by B ratio. For example, for the square footing, Kempton basically provided the Nc value as 6 times 1.0.2 dA by V, and it should be subjected to a maximum value of 9. That means the NC value cannot go beyond 9. So either it can be less than 9 or a maximum of 9 depending on the dA by B ratio. So this is for square footing. Similarly, you can get the bearing capacity factor NC for circular footing as well as for rectangular footing. Okay, so I am not going into that details. You can check it from the lecture contents. Okay. Now for the given problem, what is the depth of foundation? So depth of foundation is 1.3 meter and the width of the footing is your 4 meter. So therefore, you can easily calculate this NC value as 6 times 1 plus 0.2 multiplied by 1.3 divided by 4. And what should be the value? So the value is, I hope, 6.39. Please check. And it is less than 9. Okay. That means you need to consider this value only, 6.39. Okay, so 6.39. Now, if it comes out to be greater than 9, then you have to restrict that value up to 9 only. So, we have to consider 9. So far for this problem, we have to consider the NC value as 6.39. So, therefore, this QNU, it would be CU multiplied by NC. So, 62.5 multiplied by 6.39. So that means 399.38. Now we have to calculate the gross safe bearing capacity. Now what is gross safe bearing capacity? So this is the safe bearing capacity plus the initial overburden pressure, gamma dA. Okay, so net safe plus the initial overburden. Now the net safe is again net ultimate divided by factor of safety, and this is gamma. And net ultimate we have already calculated as 399.38, and the factor of safety is given as 3 for this problem. So divided by 3 plus the unit weight of the soil deposit is bulk unit weight 17.2. 17.2 and the DF value is 1. This will be the gross safe bearing capacity with respect to a factor of safety of 3. 399.38 divided by 3 plus 17.2 multiplied by 1.3. So it will give you the gross safe bearing capacity as 155.49 ppm, and this would be the answer. Okay, so how to utilize the Kempton's analysis for a purely cohesive deposit to calculate the gross safe bearing capacity? So through this problem that we have done. Okay, so I hope so. For this session, time will not permit for solving the remaining problems. So there are 2 more problems pending. So first of all, we'll basically read the problem statement very quickly, and we'll leave these problems as homework. Okay. So problem 6 states that a rectangular footing of 2 meter by 3.5 meter has to transmit a column load at a depth of 1.5 meter. So we have to calculate the gross safe load the footing can carry at a factor of safety 2.5 against general shear field. Okay. So again, the mode of failure is explicitly mentioned in this problem. The water table lies at the base of the footing, and we have to calculate this gross safe load using IS code. The soil has following properties: cohesion 9 kPa, friction angle 30 degrees, saturated unit weight 19 kilonewton per meter cube, bulk unit weight 18 kilonewton per meter cube, unit weight of water 10 kilonewton per meter cube, and safe factors, depth factors, and different bearing capacity factors are also given to this problem. And in addition to that, one statement is given that the load is vertical and acts at the center of the footing. Okay, that means there is no eccentricity, and again there is no inclination of the applying load or the applied load. Okay, so first of all, the bearing capacity equation as per IS code 6403 1981. So this code directly gives you the expression for net ultimate bearing capacity. Okay, so in this fashion, so C NC SC DC IC plus Q times NQ minus 1 SQ DQ IQ plus 0.5 gamma B N gamma S gamma D gamma I gamma, and there is an additional term called W prime. So this W prime, so I think you are familiar with all these terms, NC, NQ, N gamma. These are nothing but the bearing capacity factors and directly given to you. ST, SQ, S gamma, these are the safe factors. DC, DQ, D gamma, these are the depth factors, and IC, IQ, I gamma, these are the inclination factors. And cohesion, you know, the surcharge, you know, you can calculate it as the effective pressure that at the foundation level, and this B is the width of the footing, gamma is the unit weight, and W prime, so this is an additional term implemented to incorporate the water table correction. So this is nothing but the water table correction factor. Okay, now what is the value for this W prime? So it would be 1 if the dW value is greater than or equal to dF plus D. Okay, and it would be 0.5 if the dW value is. Now what does it indicate? So we'll quickly try to visualize the problem. So I'm drawing here. This is the footing. This is the base of the footing. This is the ground surface. This is the depth of foundation. This is the dimension B, that is the width of the footing. Okay. Now this dW I am measuring from the ground surface only. Okay, so two possible scenarios are talked about in this in the calculation of W prime. So if dW is greater than or equals to dA plus B, that means depth of the foundation plus the width of the foundation. So this is the possible influence zone. So then you have to take it as 1, as if there is no correction for the water table. And if this dW is equal to dA, that is for the present scenario, you have to take it as 0.5. Okay, and please keep in mind that dW I am measuring from the ground surface only. So you can take the reference level at the base of the foundation also. So in that case, W prime would be 1 when dW is greater than equals to B, and it would be 0.5 when dW equals to 0 if you take the base of the foundation level as the reference or as the data. Okay, and in between, if the water table lies in between, so suppose here, so that is dW is A plus D and DA. So in that case, you have to linearly interpolate. Okay. So for calculating the W prime, you have to linearly interpolate in between 1 to 0.5. Now this is not the scenario for the present problem, since the water table is located at the foundation level itself. And for calculating Q, so this Q would be the effective overburden. Okay. So suppose the dW is something like here. So this dimension is your dW, and suppose this dimension is your A in the sense dF minus dW. Then this part is submerged, so you have to when you will be calculating the effective overburden, so you have to take the bulk unit weight for calculation of stress for this this part dW, and for this part A part dF minus dW, you have to consider the submerged unit weight part. Okay. So in this way, the second term you have to modify. So Q is nothing but the effective overburden at the foundation level. Now this problem becomes very easy and straightforward. So all the data are with you. Only you have to calculate the W prime, water table correction factor, and it will be 0.5. You can clearly state, because the water table is at the foundation level. So it would be 0.5. Then B value, this is 2 meter. Okay. And S gamma, D gamma, I gamma, then SQ, DQ, IQ, SC, DC, IC, all are given. NC, NQ, N gamma given. Q you can easily calculate. It will be this 18 multiplied by the depth of the foundation, that is 1.5 meter. This is DA. Now what you have to do, that this gamma, this will be gamma sad for the present problem. Why? Because now the water table is at this location, the foundation level. So in this location. Okay. So that's why this will be gamma sad. So it will be completely saturated, and this value is 19. So you cannot take it as submerged or bulk, and again you cannot implement the water table correction factor. So as you are implementing the water table correction factor, so it will be taken saturated. Okay. Okay. So I will not solve this problem in its full length. So as I have explained, so please do it your own. So if you face any difficulties in solving this problem, please let me know in the upcoming session. Okay. So I hope now this problem becomes very easy. Just you have to substitute the values in the appropriate position. Okay. Okay. So this is for problem 6. Now coming to problem, the homework problem which we have originally chosen. So this is a square footing of 4 meter side is placed at 1 meter depth in a sand deposit. The dry unit weight of sand is 15 kilonewton per meter cube. The footing has an ultimate bearing capacity of 600 kPa. Consider the depth factors dq, d gamma 1 and the bearing capacity factor n gamma 18.75. This footing is placed at a depth of 2 meter in the same soil deposit. Now for a factor of safety of 3, as per Tirjagi's theory, the safe bearing capacity of this footing would be. So in this problem, you can visualize two scenarios. So first of all, scenario 1, and secondly scenario 2. Now in scenario 1, the footing is founded at a depth of 1 meter, whereas in the scenario 2, this footing is now founded at a depth of 2 meter, that is twice of the initial depth. Okay, the depth of foundation is increased. Now what you have to do, the bearing capacity corresponding to the ultimate bearing capacity corresponding to the first scenario is given as 600 kPa. Now you have to calculate the safe bearing capacity for scenario 2 with a factor of safety of 3. Now, what should be your approach? So the approach should be, since the shear strength parameters are not directly given to this problem, and this is a sand deposit. So as per Terjagi's theory, and again it's a square footing, so the expression for QU would become 1.3 CNC plus gamma df NQ plus 0.4 gamma b n gamma. Okay, and dq d gamma depth factors here it is given as 1, so no need to bother about that. So since this is a sand deposit, so first component will not be there, so it will vanish, so only second and third components will be there. And this gamma value, it's given as 15 km/m². Now df, it's varying from scenario 1 to scenario 2. So in scenario 1 it's 1 meter, and in scenario 2 it's 2 meter. What is b? Now b, this remain constant. Okay, so this remains constant, so it is 4 meter. Okay, then what is n gamma? So n gamma is given as 18.75. Now what is nq? So nq, this is the only unknown for solving this problem. Okay, so this value, this is unknown, that first you have to determine from the by utilizing the given data. So as the ultimate bearing capacity of the corresponding to the scenario 1 is given, so you can utilize that data to determine the NQ, and this NQ would remain same for the second scenario, as the footing is basically placed in the same soil deposit. So you are basically you are not changing the soil condition, so the soil deposit would remain same. So therefore you can use the same NQ value for scenario 2, and again all other entities are given to you, so you can easily calculate the safe bearing capacity corresponding to scenario 2 with a factor of safety of 3. Okay, so this is the homework, and in addition to that you have to solve problem 6 also. So this was for today's session. So the next session would be on next Sunday, that is 20th of August, and from 5 p.m. So in this week we have mostly learned about different bearing capacity theories and its application. So to name a few, we have seen the Terjagi's bearing capacity theory, Meyerhoff's bearing capacity theory, Skempton's theory, and the IS code method. Okay, so apart from that, there are many more theories like basic Henshin and this SPT correlation, that also you can explore at your home. Okay, so I'll request all of you, so please go through the lecture materials and solve the homework problems and the assignment problems, and if you face any difficulty, please let me know in the upcoming session. So if you have no problems or doubts, then we'll wind up this session here. Thank you for attending this session.